It is a great honor to present our study at Listen to Author section on KJR Online. This is Wooil Kim, and here I'm going to present our study named Novel Resectable Myocardial Model for Myectomy Rehearsal in patients with Apical HCMP using hybrid 3D printing and silicone molding method. Please refer to the email shown for further inquiry. Apical HCM comprises about 8% of all hypertrophic cardiomyopathy cases and mainly treated with medical management. However, for severely symptomatic patients with diastolic heart failure unresponsive to medical treatment, transapical myectomy to increase LV and thus volume and stroke volume has been a promising option, yielding symptomatic and hemodynamic improvement and potentially improve survival outcome compared with patients waiting on the transplantation list. Let me give you a brief outline regarding the surgical technique. Preoperative cardiac MR on the left panel shows obliteration of LV apical cavity, and this dashed line on illustration depicts target site of myectomy. The postoperative cardiac MRI in the same patient demonstrate the enlarged LV cavity after apical myectomy. However, in reality, transapical approach for myectomy has only low incidence, potentially due to a steep learning curve with paucity of experienced surgeons and also unsecured intra and intra-observer reliability in the extent of resection. Therefore, in this study, we aim to develop surgical platform enabling simulation of transapical myectomy, taking advantage of 3D printing in cardiovascular surgery. Previously, our group reported a 3D printing model to guide both transapical and transaortic approach in a patient with asymmetric septal hypertrophy. However, the model more focused on reproducing anatomic details, so could not provide meaningful surgical manipulation due to physical rigidity of the model itself, although we used the softest 3D printing materials available at the time. In contrast, other groups introduced silicone material to develop surgical simulation model for aortic valve and proximal aorta procedures, allowing relatively easy surgical management. However, as you can see in these images, anatomic details such as coronary artery, which should be meticulously considered, could be not reproduced in these models. So, we thought that there is lack of proper 3D printing material and printing method which can balance both anatomic details and enable surgical manipulation. To balance the anatomic reproducibility and surgical manipulativeness, we hybridized the 3D printing with silicone molding technique. We'll provide more details how we did it. This diagram shows our workflow for 3D printing process. The first step was basically image acquisition and post-processing for 3D printing, followed by computer-aided design. We obtained ECG synchronized CT with retrospective gating technique and segmented the cardiac chambers and vessels at the end-diastolic phase. Using CAD, we designed LV molding using outward pixel dilatation and subtraction of LV chamber. Also, to prevent deformation during silicone injection into the LV molding through the inlet, we implemented internal lattice structure into LV molding itself, and also designed cap-like internal and external support structures. Other than LV molding itself and supporting structures, anatomic details such as ICD wire and coronary artery were maintained as they are. The second step was actual printing of LV molding, internal and external structures, and removal of supporters using a water jet gun. After assembling all the structures, silicone was injected using mixing gun into LV molding, and we dried those in in the room air for 24 hours. We repeated these processes for 3 patients with apical HCM, and to verify the anatomic consistency of our 3D printed model, we obtained CT of the model and compared the thickness of LV wall and volume of the LV chamber with preoperative cardiac CT obtained from the patient. Each model of 3 patients were provided to the surgeon for myectomy within 1 week before surgery, and we could compare the resected volume and weight of silicones with those of myocardium after actual operation based on the known density of silicone and myocardium. Now we will demonstrate each case. Our 3D printed model could be freely rotated for observation from any angle, which was quite helpful for designing individualized surgical plans according to different hypertrophic interventricular septal phenotypes. This allowed preoperative planning with both transaortic and transapical approach applied for case 1. These are actual surgeon's view captured during transaortic and transapical approach for myectomy, and the resected muscles are demonstrated at the right upper panel. These figures obtained from the case 2 show CAD design showing the LV molding with internal lattice structures and inlet and outlet for silicone injection, also the course of the coronary artery and the cap-like supporting structures. With our resectable 3D model, the surgeon could intuitively recognize the essential details affecting the surgical process of transapical myectomy, such as the incision site for ventriculostomy and the location of papillary muscles. In this scheme, the 3D printed mold was constructed on a 1:1 scale, which allows surgeons to practice operative rehearsal from the transapical perspective. In this actual surgeon's view, recorded during myectomy, we can find a lot of similarities provided during mock myectomy simulated with our 3D model. These representative CT images obtained from the myocardial model verify the structural consistency of the myocardial model compared with that of the cardiac CT images. We also measured and compared the myocardial thickness between the cardiac CT and CT of 3D model. The difference was negligible for basal and mid segments, but quite considerable for apical segments and apex. All the patients showed symptomatic improvement after surgery, and postoperative echo found significantly improved end-diastolic volume. The volume and weight of resected silicone and actually resected myocardium were quite similar. While developing a new 3D myocardial model which well reflects the anatomical details of the heart, our model was soft enough to perform surgical rehearsal, and this is the very strong point of our 3D model. However, our model could not overcome the inherent weakness of 3D printing, such as time and labor-intensive workflow and relatively high cost. Also, there was discrepancy of wall thickness for the apical segments, which is probably due to insufficient removal of the supporting material because it is located in the most deepest aspect of LV cavity. So we learned lessons that supporting material should be removed meticulously with great caution with water jet gun. Again, we could balance the anatomic reproducibility and surgical manipulativeness by hybridizing 3D printing with silicone molding technique. And we believe that this could be a nice technique which might be introduced in many ways for other applications of 3D printing model in cardiovascular surgery. necessitating both anatomic details and surgical manipulativeness. Thank you for watching our video. Thank you.